Hello everybody. Today I am continuing the buckling of thin plate and it is the lecture number 2 of the module 6. So, today I will start the buckling of thin plate. You are very much familiar with the buckling of columns in your undergraduate courses, but there is some difference between the buckling of column and the plate that I have told earlier also, because when the column buckles, that means buckling load of column is the failure load that is taken in design. But in case of plate, we have seen that once the plate buckles, the post buckling strength is also higher. So, another important observation in buckling of plate is that when the column buckles into a waves, that is when the critical load is reached, for example, a column with hinged ends, when the critical load is reached, then only one half wave is formed just to transform the straight configuration to band configuration. In that critical stage 1, this half wave is formed, but in the plate it will be shown that due to its two-way action, it is not necessary that the half wave number of half waves that should be formed at critical load is equal in two directions. So, that is the peculiarity of the buckling of plate, and let us see the detail. Okay. So, buckling of rectangular plate we have taken, and for first case I have taken a simply supported boundary condition along the all edges. Now, when the rectangular plate is simply supported along all edges, that boundary condition is popularly known as Navier condition, and Navier proposed a series solution for that, and therefore, the solution becomes very easy according to if we take the help of Navier's double trigonometrical series. Okay. So, today's lecture we will find out the buckling load of a rectangular simply supported plate subjected to uniform compression along one direction, illustration of the theory by numerical examples, and I will also demonstrate one problem when the plate is subjected to biaxial compression also. Although the illustration is done with a uniform compression, but the general formulation that I have derived in the earlier class can be used to solve a problem of rectangular plate with biaxial compression as well as the shear loading also, membrane shear loading. Okay. So, here you are seeing in this figure a rectangular plate is subjected to in plane forces n x in the x direction, n y in the y direction, and n x y is the membrane shear force acting along the edges. Okay. So, these are the membrane forces n x, n y, n x y, and the equilibrium equation connecting the membrane forces is known to you, and it is similar to this plane stress equilibrium equation. Now, if I consider the action of in plane load as a fictitious load on the plate, then we write the equation of the plate subjected to simultaneous bending and stretching, that is the action of simultaneous action of this transverse load and in plane forces. Then we can write it d del 4 w equal to q x y plus n x del square w del x square plus 2 n x y del square w del x del y plus n y del square w del y square. Now, here del 4 is the biharmonic operator that you know it, and then again I am telling it, it will be del 4 by del x 4 plus 2 del 4 by del x square del y square plus del to the power 4 by del y to the power 4. Now, here in plane normal forces are tensile, therefore, we get this equation, and resultant shear force produce diagonal tension. But in case of buckling, compression has to be there. So, therefore, we reverse the sign of in plane forces, we get the equation of buckling provided the transverse load is taken as 0. Okay. So, now the equation for buckling is done by taking q x y equal to 0 in the differential equation, earlier differential equation, and the sign of the membrane forces are reversed. Previously it was taken positive, now it is taken negative. Therefore, the governing differential equation of the buckling of thin plate becomes like that: del 4 W plus n x by d del square W by del x square plus n y by d del square W by del y square plus 2 n x y by d del square W by del x del y equal to 0. You can see in the earlier equation, here in the right hand side n x, n x y and n y were appearing. Now, if I take the sign of n x, n x y and n y as negative, then it will be transferred as a positive quantity on the left hand side, and if I divide both sides by the flexural rigidity of the plate D, then we get this equation. So, this equation is the equation of buckling of a rectangular plate, thin rectangular plate. Of course, we have assumed the thin plate assumptions. Okay. Now, to find the critical load on the plate, we shall first use this analytical method using the Navier series, because Navier series is suitable for a plate which has all 4 edges simply supported. Of course, there is another classical boundary condition or classical approach, that is known as Levy's boundary condition, that can be also applied to a plate which has all the 4 edges simply supported. But in case of Levy's solution, in the intermediate stage, you have to again solve a differential equation, 4th order differential, ordinary differential equation, to find a unknown function. Now, in the Navier's method, in the intermediate stage, no differential equation has to be solved. So, this becomes easier compared to Levy's method, but Navier's method, the double Fourier series is used, whereas in Levy's method single trigonometrical series is used. Okay. Now, let us see how we can solve it. Okay. We have taken a problem case where rectangular plate of dimension A and B, A is the length of the plate and B is the width of the plate. So, that A by B is the aspect ratio, okay, and it is subjected to uniaxial compression. Now, the force is compression. So, previously I have derived the equation of governing differential equation with a tensile force, you can see, and we have got this equation. Now, in this buckling analysis, we have used a compressive force N x, and for uniaxial compression I assume that N y and N x y are 0. Okay. So, differential equation of the plate now becomes d del 4 W plus N x del square W by del x square equal to 0. Now, N x is a uniform compression along the edge, and you can see this is taken as a constant. It is not a function of this variable, space variable x and y. So, therefore, this differential equation is a partial differential equation of 4th order with a constant coefficient. Okay. Now, taking the help of Navier's double trigonometric series as expressed here as W x y equal to double sum m is equal to 1 to infinity, n is equal to 1 to infinity, a m n sin m pi x by a sin n pi y by b. So, this is the double trigonometrical series suggested by Navier for solution of the plate which has boundary condition along all edges as simply supported. So, this condition is taken, this equation is taken to represent the deflection of the plate, and it represents or it satisfies the boundary condition applicable in simply supported condition. Okay. So, let us see how it satisfy the boundary condition in simply supported plate. In simply supported plate, at x is equal to 0, if x is equal to 0 edge is simply supported, then W becomes 0. Again, if y is equal to 0 edge is simply supported, then W is 0. Now, for bending moment to be 0 at x is equal to 0 or x is equal to a, or y is equal to 0 or y is equal to b, we should take the second derivative of this equation with respect to x, also with respect to y. Then we can write the bending moment function as m x equal to minus d into del square w del x square plus mu into del square w by del y square, and then mu is the Poisson ratio. Then if we substitute the second derivative of the function, again you will find that sin m pi x by a into sin n pi y by b, these two terms are appearing. So, naturally at x is equal to 0 and x is equal to a, or y is equal to 0, y is equal to b, the bending moment vanishes. So, this condition is exactly satisfied by Navier's double trigonometrical series. So, we take it as a solution of the differential equation of the plate for the buckling. Okay. Now, you can note here, for buckling analysis we have not considered any transverse load, okay, because this is a homogeneous solution of the differential equation that will yield the buckling loads, and it will, after imposing the boundary conditions, the buckling equation, the characteristic equation that forms is a homogeneous type of equation, and most of the cases you will find the equation is formed in the form of trigonometrical functions or hyperbolic functions, and these are called the transcendental equation, and solving of this transcendental equation yields multiple values of roots, so that we can get the buckling loads at different modes. Okay. But the lowest buckling load will give you the critical load, and that is taken for the design. Okay. Now, substitute the equation 3 in equation 2. If we substitute this equation into equation 2, first del 4 W has to be expanded. If you expand it, you will find it consists of 3 terms. One is del 4 W by del x 4, second term is 2 into del 4 W by del x square del y square, and third term is del 4 W by del y to the power 4. If you expand this and then substitute here, then you will find that m to the power 4 pi to the power 4 a to the power 4 into sin m pi x by a into sin n pi y by b. This term will be there, and this term will be coming due to differentiation of this function 4 times with respect to x. Okay. Then we go for the second term, that is 2 into del to the power 4 w del x square by del y square, and if I take the mixed derivative of this function with respect to x and y 2 times, then we will get 2 into m square n square pi to the power 4 divided by a square b square. So, this term is obtained after taking the cross derivative or mixed derivative. What is mixed derivative? That is the in the derivative function both differentiation with x and y appears. So, in that case the mixed derivative is to be taken as del 4 w by del x square del y square. So, w is differentiated 2 times with respect to x, and after differentiation the result is again differentiated with 2 times with respect to y, or vice versa. Okay. Then substituting 3 in 2, that equation is obtained. Okay. You can see this equation that with nx del square w del x square, the second derivative of this function is necessary. So, it is taken and m square pi square by s square term is coming. The same procedure can be applied when there is say load in the y direction. Okay. Here the in-plane forces is in the x direction, but in some problem the in-plane forces in the y direction, or there is a combination of in-plane forces in x and y direction as well as membrane shear forces, then also this function can be substituted in the original differential equation and we can get a relation like that. Okay. Now, we get here double sum m is equal to 1 to infinity, n is equal to 1 to infinity a m n bracket m to the power 4 pi to the power 4 a to the power 4 plus 2 m square n square pi to the power 4 divided by a square b square plus n to the power 4 pi to the power 4 by b to the power 4 minus n x by d m square pi square by a square and multiplied by sin m pi x by a sin m pi y by b and equal to 0. Okay. Now, you see this equation, the equation number 4. This equation is a summation of different terms and ultimately this sum renders to be a 0 quantity. Okay. So, that means, if I take say m is equal to 1, n is equal to 1, then I will get a 1 1 into pi to the power 4 by a to the power 4 plus 2 pi to the power 4 by a square b square plus pi to the power 4 b to the power 4 minus n x by d pi square by a square multiplied by sin pi x into sin pi y, that is the a 1 1. Then again it if I add another term, say a 1 2, a 1 2 is what? Say m is equal to 2, n is equal to 1. So, in the first term, if I take n m is equal to 2, then it becomes 2 into 2 to the power 4, that is 16, 16 pi to the power 4, a to the power 4. Now, here m square, so 4, then n is 1, so 4 into 1 pi to the power 4 divided by a square b square, of course 2 is there here, again here n we have taken 1. So, pi to the power 4 divided by b to the power 4 and n x by d m we have taken 2. So, it is 4 into pi square by a square into sin 2 pi x by a sin pi y by b equal to 0. So, like that you can take a different combination of terms, say m n, and then you can form the series. Okay. Now, you can see here the right hand side of the equation must be 0 and you are getting say infinite number of terms in the left hand side, which are summed up and the result is 0. Okay. Now, since sin m pi x by a sin m pi y by b for any integral value of m and n should not become 0, then each of the terms associated with the coefficient a m n should be 0. Another possibility is there, a 1 1, a 1 2, a 1 3 etcetera should be 0, that means coefficient a m n is 0, but this is not possible, because if a m n is 0, then the solution that I will get is a trivial solution. So, it will not serve the purpose of finding the buckling load. So, therefore, non-trivial solution only possible when the quantity inside the bracket that you are seeing here is 0. Okay. So, according to that we write this quantity inside the bracket, third bracket equal to 0, and you can see this these three terms can be combined, m square m to the power 4 pi to the power 4 divided by a to the power 4 plus 2 m square n square pi to the power 4 a square b square plus n to the power 4 pi to the power 4 divided by b to the power 4. These three terms can be combined to give a term, say m square pi square by a square plus n square pi square by b square whole square, and if I take pi square outside, then I will get pi to the power 4 here, and here it will be m square by a square plus n square by b square whole square, and this term remain as it is minus n x by d m square pi square by a square. Okay. So, we ultimately get that n x equal to, okay, since a m n is not 0, a m n cannot be 0. So, therefore, because two possibilities are there, one is a m n is 0 or the quantity inside the bracket is 0, but if a m n is 0, then the solution is trivial solution. So, therefore, the quantity inside the bracket is 0. So, taking this quantity to be 0 and then our target is to find the n x. So, n x become d a square pi square by m square into m square by a square plus n square by b square. So, this is the in plane force n x that we want to find, and we want to find what will be the critical load in the x direction. So, what is the critical value of n x? Okay. Now, we have to examine several conditions for finding the critical load. Okay. So, equation 6 can be arranged with some algebraic manipulation, so that useful interpretation can be done. Okay. Now, this n x, that d a square pi square by m square into m square by a square plus n square by b square whole square. Okay. So, this term can be arranged in such a way that we can get a clear cut idea that at what half wave number or what this aspect ratio the buckling takes place. Okay. The boundary condition is simply supported along the all edges, and you should mind it that if the boundary condition is changed, the buckling load is also changed, that is solution of the differential equation will be different. Okay. Now, taking a square by m square, that is a square by m square is inside the bracket. Now, if I take a square by m square inside this square term, then I will multiply this term inside the bracket by a by m, because when I take a by m outside the bracket, then it will be a square by m square. Okay. So, taking a square by m square inside the bracket, here I get d pi square, and now I multiply the term inside the bracket with a by m square by a square plus n square by b square, and then the square of this term inside the bracket. Okay. Now, divide by b square, this quantity is divided by b square and multiplied by b square. Okay. So, then the equation is not changed. Okay. So, divide by b square and multiplied by b square. So, what is done here? You see d pi square by b square, because the division by b square is taken place. So, d pi square by b square is here, and then we have multiplied by b square. So, when b square is going inside the bracket is containing the square term. So, naturally b square will be b. So, therefore, a b by m square by a square plus n square by b square and then whole square. Okay. Now, multiply each term inside the bracket. So, we are getting d pi square by b square, it is the coefficient, and then here we are getting, say, if I multiply m square by a square by a b by m, then I am getting m b divided by a. Similarly, if I multiply the second term n square by b square by a b by m, then I am getting n square a by m b. Okay. N square a by m b. Okay. So, this term is obtained. Now, this expression is very much useful, or it will be used to find the buckling load. Okay. The equation 7, if we examine very carefully, then we find that n x will be the lowest when n is 1, because the minimum value of n can be 1 only, and we want the lowest value of the buckling load, that will give you the critical load. Okay. So, according to equation 7, n x depends on aspect ratio, physical properties and m and n. M and n are what? These are integer, but this has also some physical meaning, that is the number of half waves in which the plate can buckle. So, you can see here the lowest load n x for the half wave in x and y direction is possible when n is 1. Okay. So, it is by inspection it is possible to tell that n is equal to 1 gives the buckling load, but still we do not know what is the m number of half waves in the x direction. Okay. So, lowest value of buckling load in the simply supported plate, that is in the unidirectional compression n x, can be found by letting n is equal to 1. So, that is sure from that expression, and it is certain that by putting n, because n cannot be n, the lowest value of n here is 1, then it is the integer. So, 1 2 3 like that. So, 1 is the lowest value. So, therefore, if I put n is equal to 1, I will get the lowest value of n x, okay, for n, but m is not known here. Okay. So, we have to find ways to calculate the value of number of half waves in the x direction to find the lowest load, that is the critical load. Okay. So, this is true for simply supported plate. A simply supported plate subjected to uniaxial compression buckles in single half wave in y direction, provided the compression is in the x direction. Okay. So, in the plate you have taken a plate say 1 meter by 0.5 meter for example, and the compression is applied along the direction of 1 meter, that is along the edges which have length of 0.5 meter. Okay. So, in that case the shorter edge will buckle in one half wave, that is always true for rectangular plate having simply supported condition along the four sides. But number of half waves that is required for buckling in the lowest mode has to be found out. Okay. So, how it can be found? Because the n x should be lowest for critical load. So, therefore, we differentiate this expression with respect to m and apply the condition of minimum value for m. Okay. So, now differentiating equation 7 is this, and n value equal to 1 is put here, that means we are getting m b by a plus a by m b. Okay. So, this equation is differentiated with respect to m. So, d n x by d m is differentiated and equated to 0 to find the condition for which the buckling or half wave numbers in x direction can be found out, that is we want to find m. Okay. Now, after differentiating we get this 2 d pi square by b square into m b by a plus a by m b into b by a minus a by b m square. How m square is coming? Because 1 by m, the here it is 1 by m, because here if you differentiate, first you differentiated this quantity inside the bracket. So, 2 is coming and you are getting this quantity as it is. Then you are differentiating this quantity inside the bracket, and therefore, first parameter, that is m b by a, becomes b by a after differentiation with respect to m. Then second term becomes n is 1. So, a by b, and 1 by m differentiation is minus 1 by m square. So, this value is obtained. Now, this is equated to 0, and obviously, this is valid if this quantity is 0, either this quantity is 0 or this quantity is 0. That means, m b by a plus a by m b is 0, that is one possibility. Other possibility is b by a minus a by b m square is 0. Both the possibilities can be there, but thing is that if I take m b by a plus a by m b equal to 0, I will get the absurd value of m, which becomes a negative, and negative integer is not possible. Okay. M and n are positive integers. So, the second quantity, that is b by a minus a by b m square, must be 0. So, equating these to be 0, we get m is equal to a by b. Okay. So, now it is clear that number of half waves in the plate is a by b, that is the aspect ratio. So, since simply supported plate must buckle into a whole number of half waves, a by b must be an integer. So, a by b is an integer now, because m is integer value. So, it cannot be the other than integers. So, n is equal to 1, that we have earlier found. So, for number of half waves in y direction is 1, that is decided. Number of half waves in m direction according to our formulation, we have found it a by b. So, it is m is equal to a by b. Okay. What is a? A is the length of the plate and b is the width of the plate. Now, question arises whether the aspect ratio is always an integer value. The answer is no, because the plate length may be 2 meter, width may be say 1.5 meter, or plate length may be 3 meter, width may be 2 meter. So, integer value is not always possible. There may be a non-integer value also for this aspect ratio. So, therefore, we have to further investigate what should be the value of m if a by b is not an integer. Okay. So, let us proceed towards that. So, what we get it after substitution m is equal to a by b. Suppose m is equal to a by b is your number of half waves required for buckling, then you can substitute this m is equal to a by b here and n is equal to 1. So, what you will get if you substitute m is equal to a by b, then this function, this term is 1, and if you again substitute m is equal to a by b, this is also 1, of course, n is 1. So, 1 plus 1 is 2, 2 square is 4. So, therefore, we get the buckling load for such a case is n x is the uniaxial compression that we have in our problem, it is existing, and its critical value for a by b, m is equal to a by b is equal to 4 d pi square by b square. So, this is true when the length of the plate and breadth of the plate, width of the plate, the ratio is such that it becomes an integer. For example, the length of the plate is 6 meter, the width of the plate is 3 meter, then m is equal to 2. So, this is an integer. So, this value can be used. So, suppose the length of the plate is say 1 meter and the width of the plate b is say 0.5 meter, then also it is an integer. So, this value can be used, but for non-integer value of a by b, we have to further analyze it. Okay. So, let us see. Now, it is decided that in case of simply supported plate, simply supported mean all edges are simply supported, okay, all 4 edges are simply supported, and this in plane forces or n x, that is the force in the x direction, is applied at the boundary, this compression, and it is constant. Okay. So, number of half waves that is required to be formed for finding the critical load of such a plate is 1. So, plate buckles in y direction in single half wave, that is clear, but number of waves that is required in this x direction in the longitudinal direction or lengthwise direction, that is equal to a by b. So, a by b is the aspect ratio and this is a and this is b. This is an integer, then we can get, suppose a is equal to 4 and b is equal to 2, 4 meter and b is equal to 2 meter. In that case, the 2 half waves are formed, but this is not always true. So, let us see what we can do. Okay. So, how to find the buckling load when a by b is not an integer. Okay. So, as before, n is equal to 1 leads to the smallest value of n x, that is the plate buckles in a single half wave in the y direction, that is sure. To determine the buckling pattern in x direction, let us examine how k varies with aspect ratio a by b. Okay. K is the buckling stress coefficient. Okay. K is the buckling stress coefficient. What is buckling stress coefficient? This value d pi square by b square. Okay. And if I take this m by b by a plus n is 1, n is always 1 for rectangular plate simply supported along all edges and compression is in the x direction, then n is 1. So, buckling coefficient we can find out, and buckling load, critical load will be k d pi square by b square. You can see here the critical load of the plate depends on the width of the plate. If it is compressed in the lengthwise direction and there is no dependency on the length. This is the difference between the buckling of plate with the column, because we have seen that in column the buckling load depends, or you know the Euler's buckling formula, the critical load depends on the length of the column, but here it is not, it is depending on the width of the plate. Okay. So, number of half waves in the x direction is required now for any non-integer value of a by b. Okay. So, buckling coefficient k is introduced here and critical value of n x is written as k d pi square by b square, where k is m b by a plus n square by a into m b, and n is equal to 1, that is we already determined. So, actually k is nothing but m b by a plus a by m b whole square. This is the value of k. Now, we require to find m. Okay. We represent graphically how k varies with the aspect ratio. So, in the x direction we plot the AB, a by b ratio, and the y direction it is the value of k. Okay. So, for m is equal to 1, for different values of aspect ratio 1, 2, 3 and any non-integer value also, we have plotted the curve for k. So, this is the curve for m is equal to 1. The curve is for k. So, m is equal to 1, the lowest buckling load is 4, coefficient is 4. So, that means when a half wave number in the x direction is 1, then again we can find the buckling load of this by taking this critical load by taking k is equal to 4. Okay. N is already 1, that we have determined earlier. Now, for m is equal to 2, if I plot k against a by b ratio, I will get a curve like that for m is equal to 2. This curve is for m is equal to 2, plotted here by substituting m is equal to 2 and varying a by b ratio. So, a by b ratio we are varying here along the x axis, and we have gone up to higher values. For very long plate a by b ratio is high, and up to 4 we have plotted. Okay. So, now you can see that two branches of the curve for which m is equal to 1 is taken for first curve buckling coefficient, and m is equal to 2 is taken for the second curve of buckling coefficient. They intersect at some point. Okay. Now, similarly for other m we can draw it and we can get the curve neglecting the upper portion of the curve. So, say the buckling curve is now taken like that, then this is like that. So, these are the buckling curves which are formed by joining the lower branches of the curve. Okay. Now, you can see that the m is 1, this is the curve for buckling coefficient when m is number of half waves in x direction is 1. So, this curve is valid for a by b ratio less than root 2, that is 1.414. So, if a by b ratio is less than 1.414, you can use this curve, that means here m is equal to 1. That means, you have to put the value of m in the buckling coefficient as 1. Okay. For example, here if you get, say for example, here it is 1.2, okay, aspect ratio is 1.2. So, in that case the buckling stress coefficient, critical stress coefficient will be slightly higher than 4. Okay. At exactly at 1 it is 4. Okay. Now, if I see a value, for example, buckling m is equal to 2, for any integer value of this m, we have seen that critical stress coefficient or buckling stress coefficient is 4. Okay. So, here again it is conforming to the result. Okay. Now, any other value in this curve. So, m is equal to 2, this is the curve for m is equal to 2, buckling coefficient for m is equal to 2, and this curve has to be considered for finding the critical stress for the plate within the aspect ratio root 2 to root 6. Okay. Like that it will go, and at a very higher value of a by b ratio, you will get that this buckling stress coefficient is almost nearly 4. Okay. Now, let us see. So, it may be seen that for a by b m, the buckling stress coefficient is 4, that we have calculated, and here the solid line obtained by connecting the lower branches of the various curves gives the critical value of k as a function of a by b. In addition, the solid lines indicates the number of half waves into which the plate buckles, corresponding to a given a by b ratio. Okay. Now, the buckling of the plate that may occur in m half waves in x direction, limited by a by b, which is given by the intersection of k curves. These are the k curves. Okay. These are the curves for buckling coefficient k, drawn for m and m plus 1. You have seen that any consecutive value of m that we take, say m is equal to 2, m is equal to 3, and here we find the point up to which the buckling coefficient can be found, considering m is equal to 2. Then again from here to here, intersection of this m is equal to 3 and m is equal to 4, we find that buckling coefficient is valid for m is equal to 3. So, that pattern is seen from the graphical representation. Okay. So, now if I see that mth curve intersects with m plus 1th curve. Okay. So, we can write an equation m b by a plus a by m b, there is a buckling stress coefficient without square, equal to m plus 1, that is the next buckling curve, m plus 1 b by a plus a by m plus 1 by b. Okay. Remember that k is equal to m b by a plus a by m b whole square. Okay. Now, let us solve for a by b. Okay. So, let a by b is equal to r, then we can write here m by r, then r by m equal to m plus 1 by r plus r by m. Multiply both sides by r, then we get m plus r square by m equal to m plus 1 plus r square by m plus 1. Okay. So, this quantity is found. Now, we want to solve for this r. How it is r is solved? This equation, very simple equation, from which the r square is taken out and 1 by m minus 1 by m plus 1 equal to 1, from which we get r is equal to, r means what? R is the aspect ratio a by b equal to root over m into m plus 1. So, this is the value of aspect ratio for any non-integer aspect ratio which corresponds to m, and this may be non-integer also. Okay. So, for example, the buckling stress coefficient k is obtained from the curve for m is equal to 1 for all plates a by b less than root 2. So, a by b less than root 2, buckling stress coefficient can be obtained for m is equal to 1. Similarly, buckling to occur in m is equal to 2 half waves in x direction, A by B ratio should lie between root 2 and root 6. Now, one thing you should note that the number of half waves that we have taken in y direction is always 1 for this condition, that is boundary condition is that all edges are simply supported and the plate is compressed in the direction of length. So, that condition is when this condition is valid, then we get one half wave in y direction. Y direction is the width direction, that is the shorter dimension, the longer dimension is A. Okay. Now, for A by B greater than 4, there is little variation of k with A by B, there is not much variation, and for the purpose of calculation the critical stress coefficient for such a plate can be taken as 4 without any hesitation, and you can find the buckling load. Okay. So, critical stress, we have found the buckling load n x. Now, let us see what is critical stress. The n x is the force per unit length. So, when we divide this n x by h, because all the quantities in the plate are expressed as whether it is a force, bending moment, etc., it is expressed per unit length. So, n x is also force per unit length. That means, if sigma x is the stress along the x direction, normal stress. So, sigma x into h into 1, h is the thickness of the plate, will give you the n x. So, therefore, the sigma x, which is the critical stress in the x direction, can be found as sigma x critical k d pi square by b square. Here actually we have to divide it by h. Okay. Now, substituting d as E h cube by 12 1 minus mu square, where mu is the Poisson ratio, we can find that the critical stress becomes k pi square E I, not I is there, k pi square E divided by 12 1 minus mu square 1 by b by h square, because when h cube term is there, and here for critical stress the division by h is necessary. So, h cube will become h square, and then when we transfer in the denominator, it will be in the form of b by h square. So, the critical stress here you can see it depends on the ratio of the width to thickness of the plate. So, critical stress in the plate, there is a in the thin plate, rectangular thin plate, depend inversely proportional to b by h ratio, square ratio. So, if we compare the critical load of the column with the critical load of the plate, we can see that critical load of column is a coefficient C pi square E divided by L by R square. In both the cases, you can see that critical stress depends on the material properties, that is E. E is the most important parameter which influences the critical load. Then in case of plate, you are finding the this non-dimensional parameter which is b by h square, but in case of column it is found as L by R square, because R is the radius of gyration which is coming from the moment of inertia term. If you recall that critical load of the column is nothing but pi square E I by L square, where I is the second moment of area, and that can be expressed as I is equal to A R square, where A is the cross sectional area. Then we get this critical load of the column as L by R whole square. So, this difference you can note, the critical load of the plate does not depends on the length, it depends on the width of the plate. On the other hand, the critical load of the column depends on the length of the plate. Okay. Of course, the boundary condition is the most influencing factor for both the cases, whether you calculate the critical load for this column or critical load for plate, the boundary condition is the most important factor. because you are now considering the boundary condition which is taken as simply supported along the 4 edges. If I alter the boundary condition, suppose for example, boundary condition is fixed along the all edges, naturally buckling load will be different. So, similarly in the column which has the pinned end, the buckling load is the standard Euler load pi square E I by L square, and in the critical stress parameter it can be written pi square E by L by R square, where C is actually the constant term. This constant term actually is dependent on the boundary condition. For say other condition of boundary, say fixed boundary, this will be different. For one end fixed, other end free, that C will be also different. But here you are finding that this expression is only valid for the boundary condition which has simply supported condition along the 4 edges. No other boundary condition is to be applicable for that plate, because K is here is taken according to that condition. Okay. Now, let us see some exercise chapter that I have now discussed. So, first is comparison of different factors that affect critical stress of plate and column. So, that factors I have discussed also in between the lectures, and you have noted down also. I will give these important points for that question also. Second question is the buckling load calculation for a rectangular plate simply supported on all sides, compressed in x direction for different say length and width. So, A is 750 mm, B is 450 mm in one case. Second case, A is 500 mm, B is 500 mm. Third case, A is 800 mm, B is 190 mm. Now, one thing we can see that here in the second case, A is 500 mm, B is 500 mm. So, A by B ratio is 1, that means aspect ratio is 1. For any integer aspect ratio, we have found that critical stress coefficient is 4. So, here we can use the coefficient 4, but in that case when we get say A is equal to 800 mm, B is equal to 190 mm, here also we have found that A by B ratio is greater than 4, and this is termed as a long plate. For long plate, this A by ratio is treated as greater than 4, and again here the critical stress coefficient is 4. So, we can calculate the critical stress coefficient for that cases. Then another case is the rectangular plate size A cross B, that is a general dimension of the plate, simply supported on all sides, is subjected to biaxial compression. Here instead of uniaxial compression, I am considering the compression in the both directions x and y. So, we have to derive the equation for buckling load if load ratio n x by n y is r. Load ratio means ratio of the compression along the x direction and along the y direction. This is the ratio, and we have to find for a square plate and load ratio is 1, the buckling load value given the numerical parameter like that. Thickness of the plate is 8 mm, side length is 600 mm, and E is 2 into 10 to the power 5 Newton per mm square. Poisson ratio is taken 0.25. Okay. Now, let us see the comparison that I have given in the first case. In both column and plate, critical stress are directly proportional to modulus of elasticity of the material that you have observed, and inversely proportional to the square of the dimension of the two lengths. In case of plate, the two lengths are width of the plate and thickness if the compression is along the length. Okay. Then in case of column, the dimension, that the ratio of two dimensions are, one is the length of the column and radius of gyration. Okay. So, this difference you have noted. Now, in case of column, critical stress is inversely proportional to the slenderness ratio, whereas in case of plate it is inversely proportional to the square of the width to thickness ratio that we have observed from the derivation. Thus, in case of column, length is influencing the buckling load, whereas in case of plate, critical stress is dependent on width of the plate and independent of the length. In columns, at critical load, bend configuration contains one half wave, that is, the buckling takes place from straight to bend configuration. Just when the straight configuration ceases, this is the point we take it for critical load. So, in the bend configuration, one half wave is formed in case of column. For simply supported cases, the half wave is clearly the sin m pi x by L, but in case of plate, you have seen the number of half waves depends on the aspect ratio. So, that are the difference that we have noted from our analytical work. Okay. Now, let us see the second problem. Second problem is calculate buckling load for a rectangular plate simply supported on all sides, compressed in x direction, given this width of the length of the plate 750, width of the plate is 450. In one case, another case 500 by 500 plate dimension. Thickness of the plate in all cases are say thickness of the plate we can take is thickness of the plate 20 mm. Okay. So, this modulus of elasticity this 2 into 10 to the power 5 Newton per mm square. Okay. So, these are the things that we derived in this class. The critical value of the buckling stress is k d pi square by b square, and a by b equal to in general m into root over m into m plus 1, and k is m b by a plus a by m b whole square. Okay. Now, let us see the first problem, okay, first case. Here the thickness of the plate instead of 20 mm, I have taken for calculation purpose 8 mm, because 20 mm plate is too thick and the thick plate behavior may come. So, therefore, for thin plate buckling I have taken change the thickness of the plate as 8 mm. Okay. Now, take case 1. Case 1 aspect ratio is a by b is 750 by 450. So, it is 1.67. From the chart we can find that 1.67 a by b ratio, this is 1.414 root 2. So, if it is 1.67, then m is 2, m is 2, it is obvious that m is 2. So, therefore, substituting m is 2 in this expression, we can get this k is 4.13, or from graph also we can read it if the graph is drawn accurately. Okay. So, once the k is known, then buckling critical stress can be found with the help of this formula k pi square e divided by 12 1 minus mu square, mu we have taken 0.3 into this 1 by b by h square. So, b is 150 and thickness of the plate I have taken 8 mm. So, after calculation this comes as 77.46 MPa. So, this is the buckling load of the plate. Okay. The third problem, that is the biaxial compression. Let me solve it and show you the solution step by step. In the third question, we have a plate, rectangular plate, dimension is A and B, and both all sides are simply supported. So, this is simply supported, this is also simply supported. I am giving the symbol S instead of drawing the dotted line, and it is compressed. Okay. So, this is our x axis and this is y axis, and also in the y direction this compression exists. From the discussion done in today's class and also the knowledge that you have gathered earlier in the theory of plates that I have discussed, I think you will be able to understand the procedure for solving this problem. Okay. So, plate equation is d del 4 w plus n x del square w del x square, because two directional in plane forces are there. So, I also include this equal to 0. This is the equation for the buckling of the plate. Okay. Now, for this plate which is simply supported on all edges, we use this Navier series. Okay. And m and are integer, it may varies from 1 to infinity. Now, substituting this in this equation is substituted here, and after substitution we get this value, that is again double summation a m n minus, I have divided both the sides by d. So, here I will get n x by d m square pi square by a square plus n y by d n square pi square by b square, and then sign functions are appearing. Equal to 0. Okay. So, after substituting this we arrive at this equation. Okay. Now, naturally for non-trivial solution of this buckling load, we have to obtain that m square pi square by a square, n square pi square by b square whole square equal to n x m square pi square by a square d is there, n y n square pi square by b square d is there. This equation is obtained for non-trivial solution. Now, from that equation, if I take n x by n y, that is the load ratio, take this is equal to r. Okay. So, if I take this is r, then I can write n y m square pi square by a square d n x by n y plus n square pi square b square d, and right hand side I can write the pi to the power 4 m square a square plus n square by b square whole square. Okay. Now, taking this n x by n y equal to r, then I can transform this equation as n x by r, then I can write here r m square pi square a square d plus n square pi square b square d, and this side is pi to the power 4 m square by a square plus n square by b square whole thing square. Okay. Now, our target is to find n x. Okay. So, from that equation n x is found as, after simplification you can see also m square by a square plus n square by b square whole thing square pi square, d will be here, and then in the denominator it will be m square by a square plus n square by r b square. Okay. So, this is the value of n x in terms of load ratio. R is the load ratio and a by b will be width ratio, aspect ratio. Okay. Now, we have to solve a problem of square plate. So, let us take this. For square plate, a by b is equal to 1 and we have taken load ratio as 1 for this problem is equal to 1. There is r is equal to 1, load ratio means r. Okay. Now, after substituting this, we in the previous expression that for n x, we now get n x equal to m square n square pi square d by a square. So, simple expression is now found for n x. Now, this is lowest. What will be the lowest value of n x for what m and n? For m is equal to 1 and n is equal to 1, because these are constant parameter, the n x will be lowest. So, critical value of n x is now obtained as n x is equal to, say substitute m is equal to 1 and n is equal to 1, we get 2 pi square d by a square. Substituting d as if I take d as 12 e into h cube, h is the thickness of the plate divided by 12 1 minus mu square, mu is the Poisson ratio, we can get now this will be equal to pi square e divided by 6 1 minus mu square into 1 by a by h square. So, this is the critical load, this is not the critical stress, I should call it critical stress. Okay. So, critical stress is obtained like that, and now this for substituting the numerical value, one can calculate the critical stress for this plate. Okay. So, thank you. I think you have understood how to proceed to calculate the critical load of a thin plate subjected to uniform compression as well as biaxial compression, but I have taken a special case where the load ratio is 1 and aspect ratio is also 1 corresponding to a square plate. Okay. Thank you very much. Okay.